This video describes the initial setup and use of the miniLDV. This is the box that the miniLDV comes in. It consists of a probe. We call it miniLDV probe. And the probe has marking on the side as a serial number. And then it has miniLDV 240, and this is the standoff distance of the probe. This is the safety and cleaning cap for the miniLDV probe. The cable has a electric connector and a fiber optic connector. The miniLDV comes with a box that is called processing engine, and it has a key, a locking key for the safety of usage of the instrument. In the back, there's a place for the electrical connection to the probe. There's a place for the fiber optic connection for the probe, and there's a cap on it that is for when you disconnect the probe, you need to put this back on because the optic of the detector is right behind this. These two BNC are for detection, and we'll describe later. And then there is an input for a 12-volt DC power supply. So now I show you how to connect the system. So to connect the cable, first you connect the electric connector to the back. There are two red dots, one on the cable, one on the receiver, and you line it up and you lock it in. As far as the fiber optics is concerned, the fiber optics has a cap. Carefully take it out. Make sure you do not touch the end of the fiber. And then on this other side, on the receiver side, there is a cap on the detector that you need to take out. And there is a key on the fiber that you line up with a notch, and when it goes in, you can lock it up and it's firm. When you take it out, please put back the cap on the receiver and also on the fiber end. While in the lab, leave it connected for as long as you need, but when you disconnect it, make sure you put back the cap. There is a power supply that is provided. It's a 12-volt power supply that works with 110 and 220 volts, and you connect it to the back in the power supply input. In the back, there are two BNC connectors. These two BNC connectors and two BNC cables that are provided allows you to look at the signal on the scope if you need to. Usually you don't need to connect those to the scope. Finally, there's a USB cable that you connect in the front and you connect to the computer. We have now connected the miniLDV probe to the processing engine in the back. In this case, the probe is attached to a 2D traverse that is provided as an option, and the probe itself is attached to the traversing with a holder that is provided in your LDV kit. We've provided a humidifier as a flow field, and as you can see, the flow is going from the top, from the below to above. And if you zoom here down in this probe, there is a line here, and to correctly align the system with the flow, this line should be in the direction towards the flow itself. So the flow coming from the top to bottom will undo this screw, turn this 180 degrees such that the probe is aligned in the correct direction with the marker line towards the incoming flow. If I turn on the laser, you will see that the beams, there are two beams that are coming together at the attachment area of these two probes, where the cross is the measurement location. So we align the flow to cross the probe volume in this direction, and we've connected the APD, output of the APD, to the scope. And as you can see, after a little bit of trying, you could capture a classic Doppler signal as shown here with a Gaussian envelope and a single frequency modulation of the signal. To start the program, run Mse Acquisition Manager. This is the main page of the software, and the first thing you need to do is it has a single point acquisition and a profile acquisition. So we'll start with a single point acquisition. To start the program, you need to run the setup each time you open the program. And the setup starts with a new page, and this page is the setup for the LDV probe as well as for the program parameters. To connect, you need to look for correct port setting. It usually assigns the correct port in here, but if not, you need to look for it and push connect, and then look for acknowledge here. If the acknowledge doesn't come, you repeat the process maybe 2 times and you get acknowledge. If the acknowledge doesn't come, you look at the electronic, make sure that it's on, and otherwise it should come out. Once this is on, the first thing you can do, you can check to see if you can turn the laser on. The laser comes on and it shows you a green light, and you should check the probe to see that the laser is on, and you can toggle the laser from here, turn it on or off. Now we'll talk about how to set up the parameters. The first thing you need to do is to look at the characterization sheet that is provided with your miniLDV and input the correct values here for the fringe separation. In this case, the one that I'm using is 9.2 microns. And then there is an item called frequency shift slope, which is the fringe frequency shifting calibration number here, and in my case is 284.20. These two numbers was measured or was set in the lab and never changes for the life of the probe itself. Once you do that, push set so that the software acknowledges the receipt of these parameters. In here there's a frequency shifting parameter that the stop is on. That means now the frequency shifting instrument is off because we've stopped it. I will come back here for this value later. The second group of parameters are the parameters for that relate to the flow, and we will get that once we set the flow up, and then I'll show you what these numbers mean and how to set them up. First, what you need to do is push raw signal, and it's really raw background noise with the laser off preferably. You don't have to have the laser off, but I prefer to have it with laser off. And when you run it, you will see where the background noise or background setup of the detection system is set in terms of an arbitrary number in this case. And this guider and this white line sets the threshold of your signal. What this says is that the background noise in this range, and we expect the signal to be above that. So we will slide this down such that this white line that indicates the trigger value for the system is just above the background noise. We can tweak these to get higher data rates and so forth later, but as long as it's somewhat close to the top of the background noise, I can even bring it lower now. You can get as close as you want without going into the red zone. And what I'm doing is I'm just incrementing. So we have 8352 as a number, and here you can also, for each run, you can see the maximum and minimum value of the red lines there. So it's about 8249 or 8250, and we are 8352, so we're about 100 counts above that, and that's good enough to be above the background noise.
So once we're satisfied with that, we're done with this screen, and we abort that and then close. And remember this number 8352 when we close. The 8352 number comes back into the threshold value, and this is the threshold that we start. As I said, we can then change it if we really want to. The units, I'll go over the decimation, the FFT point. The FFT point, you could run it at 1024, 512, or whatever number you prefer. The higher the number, the higher the resolution of the measurement, but then the longer the computer needs to process the data. So if you, after very high data rate, I would suggest a 256 would be good. If your data rate is not that important, 1024 will be a good number. So, and then you can leave that for the entire duration of your measurement. The unit, you can choose from a number of units shown here, from millimeter to inch to foot per second, kilometer per hour, and mile per hour. I would prefer to set it up at kilohertz, so we can set everything up in frequency domain. And once you set this up, then you can go back into meters per second. For the flow, you need to understand what the speed of your flow is. But since you have no idea, you can start by putting 0.1 kilohertz as your lower frequency, and maybe 10,000 or 10 megahertz for the higher frequency. Minimum SNR of 2 is a good starting point. You can change it as you learn more, but to get started, 2 would be fine. And the signal width is typical. I'll explain to you later. And you push set here. Once you set this page is set preliminary at this time. We can fine-tune it later, as I'll show you. But at this time, we turn the laser on, and then we'll start the flow, and then we'll take the test acquisition in a minute. Once you have set up the flow, you can start test acquisition. The test acquisition button grabs a sample according to the threshold and displays the results. And you can do a few just to see if you get a signal that looks like a Doppler burst. And this is not a very good presentation, but you can see that you have a signal that is not noise, that is modulated signal, and then in both cases. Let me explain to you these three windows. The top window shows the captured signal burst on the first signal that comes above the threshold, and in this case it was a value here, and basically from here to here is recorded and grabbed and digitized. There's a digitizer, there's a 14-bit digitizer that digitizes the signal. Once the signal is digitized, according to the mean max speed, it's filtered and then windowed, and then the processed data is shown here. As you can see, it looks like a Doppler signal, and we'll see that if the results are okay. The third window shows the FFT. The red line, if you can see it here, the red line denotes the FFT of this signal in the middle screen. The orange circle denotes the maximum peak of the signal, and the yellow signal denotes the frequency value of that signal based on the value of this SNR. Once you put your cursor in the bottom line, you will see the value of the U, or the velocity for this particle, was 141 kilohertz. And then the SNR is 9.1. You can do a number of test acquisition just to make sure, well, this is a noise, looks like a noise, this looks like a signal. And again, the numbers are not too far off, 156. Once you're familiar with this value, 156, you can then change the minimum speed somewhere below that, let's say 50 kilohertz, and maximum speed, let's say 500 kilohertz, to bracket that value. You push set to enter those numbers and take another data acquisition, and you will see the difference. The difference here is such that, first of all, The filter and the bandpass filter of the system is such that it's made the signal into a symmetric modulated signal, and this is a correct way for that. And then this signal on the top screen is processed to give you the processed data or signal that is going to be evaluated. And down here again you have the much better presentation of the FFT peak, much higher, and then still the value of the frequency is around 113 kilohertz, which is understandable. Since our flow is not very steady, you get a variation, you know, between whatever the frequency range is. Next I want to talk to you, so this is the function of the minimum and maximum speed. Let me explain to you these screen shape. As I mentioned, this is the value of the results, which shown here in kilohertz. This is the peak of the detected peak of the FFT. These narrow lines indicate the maximum and minimum speeds that you've indicated. Excuse me. If you put your cursor on this line, you will see that it's 500 kilohertz, which is the maximum speed you've set. And if you put your cursor here, is about 50 kilohertz, which is the minimum speed. The thicker line indicate the actual hardware filter. If you put a cursor here, is about 25 kilohertz, and if you put a cursor here, is about 1 megahertz. So the software has told the hardware to provide you with the closest filter, which is below 50 kilohertz. This one would be 25 kilohertz, and a low pass filter above 500 kilohertz, and the closest one we have is 1 megahertz. So this screen shows you the frequency range of the hardware. This is low pass hardware, this is low pass software, this is a high passed software, and then high pass hardware, and this is where the value is. Now if we haven't talked about decimation. The digitization of this system, of the maximum digitization rate of this system, is 12.5 megahertz. But since our frequency is at 113 or 100 kilohertz thereabouts, or less than 500 kilohertz, you would like to reduce the digitization rate to match the frequency range that you work with. The frequency range that we work with is 50 to 500, let's say, kilohertz. So we would like the decimation to be such that decimation number is the number that you divide to 12.5 megahertz. The way we're digitizing now is 12.5 megahertz divided by 4, which gives you a 3 megahertz maximum, but we don't need all these range. So we increase the digitization rate, let's say by number 16, and then we take another data, and sometimes you have to hit it twice to get that. So this is the signal that is digitized, and this is the area that is processed. Oh, by the way, in this screen, these lines indicate the signal width that is used. If you put narrow and you set it up and you do test acquisition, you will see in that it says that the amount of the signal that is processed is defined by these two white lines. So it's narrow. If we set it to wide, it will process the entire window. And you'd like to match, and we have to test. We would like to match the signal, because these are noise or other particles. So in this case, I would go with a typical. That would be probably a good choice. Oops, sometimes. Okay. So, all right. So now this is signal. This is the results. And with decimation 16, you can see that the maximum frequency is 781 kilohertz, and we are 120. We can even go to 32, and let's see what happens when you go to 32. You will see that the frequency will be take another one. Sometimes you have to hit it twice to get okay, so as you can see, it's quite variable, but it's in this range. And as long as this yellow is inside the clear area, your acceptable bandpass is good. And we can do it a few times. And you can see it's always, the dot is always in the clear area. So our setup is correct. Once we are happy with this, we push OK, and then go back to this screen to the single point acquisition and do a capture. Now what it does, it's capturing the individual samples. On top is the histogram. Every single line is one frequency, and as you can see, we are generating a histogram that is somewhat skewed, that usually indicates that the flow is not uniform and also not symmetric. So on top, this is the histogram, and we're just generating a lot of numbers. These blue lines, each blue line is indicator of one velocity measured, and then so this is the history of the measurement. The yellow line is a running average of the entire data. And then the red lines here are the RMS, or the fluctuation value of the results. And once we're happy with the data acquisition, we stop. And then the results are shown here. We've captured 42,000 samples here in about 1 minute and 1 second. Of these, we've accepted 9,000 samples. And the way we accept is that each sample goes through a number of tests, including the test of signal to noise and test of the bandpass filter. And if it's satisfied, it only accepts. If it satisfies all conditions, it's accepted and then used into the calculation of the mean. Otherwise, it's discarded. So in this case, we have a lot of samples that were discarded for some reason. We'll see that. So here it gives the mean is 131 kilohertz. We missed about 40,000 samples, and this is because we were doing a lot of calculation while many particles were coming. And usually that's not the case in normal aerodynamic or fluid mechanic measurement. But anyway, in this case, one of the reasons is that we missed so many because we were doing calculation, and I'll show you how to improve on that. The measurement has a 37% RMS, and that's because the flow is not really good. And our average data rate was about 158. So these are the results of your measurement, the main one being the speed. Now what I could do, I could go back and then go into the meters per second unit and take another data. In fact, the same data now is transferred into 1.2 meters per second. So knowing the frequency shifting. One thing here shows that the histogram is clipped on the lower end. So we need to reduce the lower end and maybe reduce the higher end as well. So I go to setup. Actually, we could have done it here in the minimum speed, but let's say minimum speed of 0.3 meters per second to 3 meters per second, and we take a test acquisition just to make sure that our filter settings and our histogram are the peak histogram is within the accepted area. And in order to take the data rate higher, we can actually have a less FFT point. As I mentioned, we will reduce the resolution, but nevertheless, the amount of calculation, as you can see, is much less, so we can do a lot faster data acquisition. So anyway, let's take another data and see how the histogram fares this one. The histogram is much better. Is not clipped on the left or on the right, and you can see fairly symmetric histogram. And we still have a lot of missed data. That's because what we could do, we could actually turn off these updates in order to reduce the amount of display and then capture, and as you can see here, it shows okay, I think there is something wrong with my software here, that these missed samples are always there, so it's probably not a real one. Anyway, here we have 4,000 samples, we have about 400 data rate, and the number is pretty much the same as before, 1.6 meters per second average speed. I can take another one just to see how consistent the results are. .67. So that's pretty good. I think there's something wrong with our software here, and this number is incorrect. These two numbers need to be correct. So ignore these two values for this demonstration. We'll fix that. That's basically it. Now you could record these measurements by choosing an either ASCII code, ASCII file, or binary file, or both as an output. I prefer ASCII file because it's easier to open it up with Excel or other programs. But first I need to place a folder on, let's say, desktop, say test, and so I go in there and then I push T1 as a first test. So now I know what the name of my file is, and browse, and then I capture, and here I stop after a little while. So I have 3,000 samples. Of that, 2,000 has been accepted. Again, these two numbers are incorrect, and then time elapsed is 5 seconds and data rate 400, but the velocity is 1.64. Now if you open the test, you will see that you have the speed header, which shows what the speed data is. We separate the header from the actual speed results. These are the speed results, and if you place them on top of each other, you will see what the you will see what these are. So the first one is the time, adjusted time, and high resolution time in microseconds, and then other parameters in there. You actually, what I should do is open them in Excel. Speed header, open with Excel. And then do the speed and Control All, copy and paste here, and so you have the device time in milliseconds. This is the actual. If you put a number here, you will see the number in year and so forth, which is useful if you need to reference two instruments. There's a high resolution, which is the microsecond. So this gives you the millisecond value. This is the relative to the trigger value, and this is relative to the absolute number. This is microsecond resolution. There's the event number. Some events have been zeroed out, so it starts with 8,000. So this number is incorrect, and these are the individual speed and individual SNR. So really these are the information that you can plot, and you can do calculation afterwards. but we'll just erase these, and I have to plug my battery, so I'll stop and then restart again. Additional information that are recorded in addition to the speed header is a statistics header, and then the configuration of the setup that records all the setup configuration if you needed to go back and check your setup afterwards. As I showed you, the speed and also the statistics, which are the results of the measurement. They're all recorded for each data point that is here, and they're all identified as T1 as I showed you. For those probes that have frequency shifting option, I would like to talk about how to set it up. You go from the single point acquisition, you push setup, and the screen is shows here as it was before somewhat. The frequency shifting parameter. The function of the frequency shifting is to allow you to measure both the direction and the magnitude of the speed of the individual droplets or particles, or to be able to make measurement in highly turbulent flows. In both cases, you do need frequency shifting, but it's an option that you can provide, but it has to be done at the time of the ordering. To set up the frequency shifting, make sure that the frequency shifting parameter or the calibration number is correct according to the characterization sheet. Unmark the stop and push set. And once you do that, the frequency shifting status should turn green, and that means the measurement that the frequency shifting has started and is correctly set at this number. You can use numbers from 3000 RPM, which is the speed of the motor, to about 10,000 RPM. Each one will give you a different amount of shifting that is provided in your characterization sheet. For 3000, for this probe, the characterization sheet shows that it has 852 kilohertz frequency shift. And if your negative velocity is not larger than, let's say, minus 500 kilohertz, this is adequate. If the negative velocity is larger, then you need to go to higher frequency shifting. And those are described in the manual. To set, you need to reset these parameters for the frequency shifting. Namely, remember that there's 800 kilohertz frequency shifting on top of your Doppler frequency shifting. So you have about a megahertz. And to have a megahertz, the maximum decimation that you could use is 4, which would mean that you're running at about 3 megahertz digitization rate. So you set that and then test acquisition. And what it does, it provides you the shifted frequency signal. Again, the processed analog signal between these two limits. And then the value of the measurement in meters per second. In this case, for this flow, it goes from 0.5 to 0.3. So maybe we want to open up here, let's say 0.1 to 5 meters per second in order not to limit our measurement. And now you can see, so you can take a few samples and look at the scope here and see that your signal is in the clear area, which is the band defined by your band pass filter. And you push OK and capture a signal. Again, we want to now go to T2, let's say, so that we don't overwrite the data before, and capture. Again, these are the numbers, so that's plenty. We stop, and this is the results. It's about 1.1 meters per second at this time, with 43% RMS, which is the flow that I showed you, the humidifier flow. And the histogram is not clipped, so this is quite nice. And the results, this is the time history of the results. One last item that I wanted to show you was this appended data and time. If you choose that, You don't need to change the name of the file each time, because the name of the file is appended by the date and time, so you never overwrite your files. So if you're making many data and you don't want to name them individually, you can physically append the data and just use the same T1 or whatever you want to use as a header of your data.